Here's the second video then, folks. So questions 11 to 20. So number 11, how many electrons form the carbon-oxygen bond in methanal, HCHO? So methanal has this structure. You've also got your lone pairs on your oxygen there. So the carbon-oxygen bond is a double bond, so that would be 2 pairs of electrons or 4. Again, if we wanted a kind of a Lewis structure, sort of putting that in where we showed it a bit more fully, you'd have the carbon's 4 electrons, and then you'd have the 6 electrons of the oxygen being in group 6, and you'd have the hydrogens with each have their 1 electron as well. So you can see the double bond is made up of 4 electrons. Between which pair of molecules can hydrogen bonding occur? So we've got CH4 and H2O. Well, water can form hydrogen bonds, but CH4 can't, because it's basically, it doesn't contain the all-important hydrogen fluoride, hydrogen oxygen, or hydrogen nitrogen bond, because remember, for hydrogen bonding we need one of these 3 bonds to be present. Where we've got the hydrogen, I've swapped around here, but the hydrogen bonded to one of the 3 most electronegative elements. We've got methoxymethane plus CF4. Well, there'd be no hydrogen bonding at all there. Methoxymethane does have lone pairs of electrons, as does fluorine, but we don't actually have any HF, OH or NH bonds. So can't be this one, not this one. CH4 and HF, well again, we've got no lone pairs of electrons. HF can form hydrogen bonds with itself, but not with methane, it's not this one. And then we've got methanol and water. Well, these substances, they can form hydrogen bonds with themselves and also with each other, because of course we could have the methane hydrogen bond into a water molecule like this. So if I put lone pair of electrons there, lone pair here, terrible shape, but that'll be fine. And then if I have my water molecule, it will form a hydrogen bond like so. So I've got lone pair of electrons on the oxygen of the methanol, attracted to the hydrogen of the OH bond. Similarly, I could also have hydrogen bonding off of the hydrogen there from the lone pair on an oxygen, down from water like so. Should put in some dipoles as well, maybe isn't drawing them out, so it'll be delta minus, delta plus, delta plus, delta minus, just have to put them all in for just a few. So there's 2 examples of hydrogen bonds, so our answer is D. Which substance has a giant covalent structure? So I'm always a little bit sort of wary with these, because you sort of think, well, if you've got graphite and diamond, the key difference between those 2 is that they both have high melting points, but diamond does not conduct electricity, whereas graphite does, because of the delocalized electrons. So looking through these possibilities, you've got melting point, solubility, and electrical conductivity. Well, I know I'm looking for a high melting point because it's a giant covalent lattice. So that's definitely not going to cut it. And 801 seems pretty low as well. In fact, as I recall, that's the melting point of sodium chloride. And sodium chloride is very soluble in water and is a good conductor when molten. So this is probably sodium chloride, although I wouldn't expect you to know that. It's just I happen to know the melting point because I'm a science teacher. These next 2 seem more plausible. So again, we've got quite high melting points now. So I'm thinking going between these 2. Solubility in water. Well, giant covalent lattices are not soluble in water. Graphite, diamond, quartz, which is sand, they don't dissolve in water, so these are both low. So again, it's another way that I could have helped eliminate those. Electrical conductivity then. Now this is in the molten state. So I'm preferring this one because it's got the higher melting point. This doesn't really help me at all. And then it's just that question mark. Okay, well, we know graphite's a good conductor of electricity. However, if we have a think about it, if it's in the molten state, that lattice in graphite will have broken down and you won't have that network of delocalized electrons. It's not like metals, which will always have those delocalized electrons. In the case of graphite, it's just the arrangement where you've got those kind of overlapping p orbitals in the 6-membered rings, where they all kind of overlap with each other. You get that kind of network of p orbitals which all overlap with each other, and the delocalized electrons can flow through those. Now if you melted the graphite down, that network of p orbitals is all broken down. So I don't reckon molten graphite would actually be a conductor of electricity anymore, because you wouldn't have this lattice that is required where you don't need it in metals. So I'm going with D, based on the higher melting point and my rationale that graphite wouldn't conduct in the molten state, because then it would be equivalent to diamond in the molten state. You wouldn't expect diamond to kind of conduct, so I'm going to go with that one. Number 14, which species has bond angles of 90 degrees? Well, eyeballing some of these, there's a few I can sort of pick out fairly sort of sharpish, like the ammonium ion. Of course, we've seen that before, and that's a tetrahedral, where we got a coordinate bond from the nitrogen to a hydrogen ion, and now we've got the ammonium ion. Silicon, same group as carbon, so again you can sort of quite quickly sort of put that one in as, well, that's tetrahedral as well, the same as carbon would be. Put the lone pairs in, if I'm drawing a valid Lewis structure. So again, we're looking at bond angles of 109.5, so that doesn't work. Aluminium tetrachloride, now aluminium's group 3, and the way you could form this ion is by accepting a coordinate bond from a chloride ion. So again, that to me would be looking like a tetrahedral, because aluminium, period is aluminium, it's in period 3, but yeah, maybe if we should kind of do our kind of more, see if the octetral bit works, where you sort of think, right, okay, so aluminium is number of our Lewis structure would be aluminium's group 3, chlorine's group 7, there's 4 of them, plus we've got a negative charge, so that's 4 times 7, 28, plus 3, 31, plus another one is 32, there's 32 electrons. If we divide that by 8, which will work here if everything's obeying the octetral, so we'll give it a try anyway, so divide that by 8, of course that's 4 bonds with 0 remainder. So again, that backs up, okay, sort of no lone pairs, your aluminium being tetrahedral. Putting the lone pairs there. Again, remember, if you're thinking, right, okay, each of the chlorines, these 3 chlorines, let's say, had 7 electrons, so there's the 6 as the 3 lone pairs, plus there's 1 here from the chlorines. The aluminium had 3 of its own, so it's put those into making these 3 bonds. This chloride must have come along with an already 8 electrons, so it must have been Cl- came in and then formed a coordinate bond to the aluminium, and it brought both the electrons with it. And here now aluminium's obeying the octetral, and we'd have our 32 electrons. Which brings us down to this last one then, ICl4-. Let's do that same trick here. So the Lewis structure would be iodine's group 7, so is chlorine, so it's 4 times 7, plus we've got a negative charge of 1. So it's 4 times 7, 28, 35, 36 electrons. If we divide that by 8, once again that's 4 bonds, but we do have a remainder this time of 4, which would be therefore 2 lone pairs. So plus remainder of 4 equals 2 lone pairs. Remember, the examiner's not going to be seeing this, he's just going to be seeing the sheet where you put the answer, so we can sort of use whatever workings we like. I'm just sort of using it to help you with the rationale here. So if we've got 4 bonds and 2 lone pairs, according to my estimation, yeah, that would be basically 6 electron domains. So 6 electron domains would be octahedral. And then remember, with octahedral, the lone pairs, as you introduce them, go in the top and bottom. So that would what we'd be coming off. So the lone pairs go up here and here for an octahedral. We'd have our chlorides off to the side. So the actual shape we see is square planar. And basically that's a bond angle of 90 degrees, as is this around the back there, 90 degrees. So this is our answer here. Okay. Number 15, what is the hybridization of the numbered atoms in ethanoic acid? You guys haven't quite done hybridization yet. We'll be doing that in the next few lessons, so I'm going to go through this quick because you just won't recognize it yet. Basically, when you're looking for sp3, you're looking for single bonds. sp2, you're looking for double bonds, and sp, you tend to be looking for triple bonds. There is an exception, however, so sp, as well as being triple bonds, it can be when there's two double bonds. So this carbon here, for example, would also be sp, which is what we see in carbon dioxide. The carbon is sp. So think, right, okay, we're looking for single for sp3, we're looking for double for sp2, and we're looking for triple typically for sp, but it can be between those. So carbon number 1 has just got the single bonds, so this is going to be sp3, and that will become clearer when we go through it in class. So that's a tick, that's a tick, that's a cross, that's a tick. Carbon number 2, you can see there is a double bond, two single bonds, so that's sp2. So this is sp2, so that's a cross, that's a tick, that's a cross, that's a tick. And then number 3, well, that's just single bonds again. You've got lone pairs there and there, so there are 4 electron domains, and there's no double bonds, no triple bonds, so this is going to be sp3 as well there. So our oxygen there is sp3, so cross, 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 and tick. So D will be the right answer, where we've got the 3 ticks in place. Number 16, we're on to enthalpy now. So hydrazine reactive oxygen, there's hydrazine reactive oxygen with nitrogen and a couple of waters. The enthalpy change is -623. What is the standard enthalpy of formation of hydrazine? The standard enthalpy of formation of water is -286. Okay, so we've given the enthalpy change for the whole reaction. We need to work out the enthalpy change of the enthalpy of formation of the hydrazine. So a way you can calculate enthalpy change, so delta H itself is that it would be the total enthalpy of formation of the products minus the total enthalpy of formation of the reactants. Okay, it's just an equation you should learn, and then if you get, normally you're using these to work out delta H, but this time we're trying to use, we've got a known delta H and we've got one of these is known to work out the other. So we're trying to work out the enthalpy of formation of the reactant. Now you might be thinking, what about the oxygen and the nitrogen? Well, their enthalpy of formations are 0 because they are elements. So we don't need to worry about those guys, the oxygen and the nitrogen, because their enthalpies of formation are 0. Because it doesn't take any energy to create an element from its elements, whereas basically the enthalpy of formation of hydrazine, what we'd actually be looking for, remember, would be taking nitrogen plus 2 hydrogens to create a hydrazine. That would be the enthalpy of formation, where you make 1 mole of a substance from its elements in their standard states. So that's what we're actually trying to find. So this is what we're looking for, the enthalpy of formation of the reactants, because we've got the one of the products. So if we kind of slot in what we do know, so this is basically, this is -623, and this equals the enthalpy of formation of the products. Now, water is the product. We've got to note this as well, there's 2 of them, so that's going to be 2 times -286, and then that's going to be minus, well, what we're trying to find, delta HF, or hydrazine. Looking at this, we can do it, but hopefully we can get the number from here, sort of again, make the maths a bit easy for yourself, sort of where you sort of think, oh well, look at these numbers across here, I've got a 572, so that makes sense. 2 times 286 is that 572, yeah, that's about right, and then they're not trying to catch me out there. In fact, it's 572 is the only one option, so that's going to be -623 equals -572 plus, and that's minus delta HF. So then if I get delta HF on its own then, so let's take delta HF over this side so it becomes positive. So delta HF, take that over the left, equals -572, bring the -623 over, so that then becomes plus 623. So that's looking like C as it's laid out. Okay. Number 17 then. So 17, we've got another enthalpy question. This time it's looking where we've got the Q equals MC delta T over N kind of thing. Well, that's delta H. So let's have a look. So we've got 5.35 grams of solid ammonium chloride was added to water to form 25 grams of solution. Maximum decrease in temperature was 14 Kelvin. What is the enthalpy change in kilojoules per mole for this reaction? Molar mass of ammonium chloride is 53.5. Specific heat capacity of the solution is 4.18. Now again, you kind of make your life a bit easier on these things if you sort of think, right, well, what is delta H? Well, delta H equals MC delta T over N. And that's also, that would be in joules per mole, because unless we had the mass in kilograms, then MC delta T would give us the energy change in joules, and we would have then divided that by 1,000 to convert to kilojoules. So divided by 1,000 to get the answer in kilojoules. So that'd be that. And then we can start slotting in some of these values then, see which ones kind of start looking correct. Now, I'm going to have to do some of this 5.35, because you might notice 5.35 doesn't feature down here, and that's because it's a mass of one of the reactants. We need the number of moles. So how do we work out the number of moles? We need to do, so your moles, N of ammonium chloride is mass over relative formula mass. So that's 5.35 grams. Helpfully, they've given us the relative formula mass, 53.5. And notice it's not too tricky as well. It's basically a tenth of it, isn't it? And again, you can kind of confirm that. You sort of think, well, here's where I'm looking for the number of moles on the bottom, and I got 3 of them which feature 0.1. So that kind of makes sense. So I do want the number of moles on the bottom, so that's going to eliminate that one, because there's no 0.1, because I need N as being 0.1, because I could actually kind of draw it out now, couldn't I? I could fill in, well, delta H equals, let's fill in some of these values. M is the mass of the solution, so the water, 25 grams, times the specific heat capacity, which is 4.18, times delta T, the change in temperature. The change in temperature is 14 Kelvin, so that's 14. And then we could divide that by 0.1 times 1,000. So is that much of any of these, or how does that look? Well, looking at this one, they've got 25 times 4.18 times 14 plus 273. They're trying to catch us out a little bit there, because they're trying to make us convert it into degrees C, but it's a temperature change. It's not actually a temperature. If they'd given us 2 temperatures, we still wouldn't have to convert them anyway, because the change in temperature is the same value, whether it's in Kelvin or degrees Celsius. So we don't need to do anything with this 273 business. So it's between these two. Now these look identical, it's just in the sign. So again, okay, well remember, if it's negative, it's exo. If it's positive, it's endo, your enthalpy change. The temperature in this reaction decreased, so it's an endothermic reaction. Energy was absorbed overall, so it must be C. Just thinking about it, do watch out on some of these ones. I say all of these feature 1,000 on the bottom because I'm using M in grams. If they ever had one where M was in kilograms, then you wouldn't have to divide by 1,000. And that's because you can have 2 sets of units for the specific heat capacity. Sometimes you see it written like this, joules per gram per Kelvin, but sometimes you see it written as kilojoules per kilogram per Kelvin. Okay, so if this had been in kilograms, it would have been already divided by 1,000. We wouldn't need the 1,000 in the bottom. 18. Which equation represents the enthalpy change of hydration of the chloride ion? So remember, your enthalpy change is basically when 1 mole of gaseous ions are dissolved in water. So we're looking for gaseous ions, so this looks like a good start. So chloride gas being dissolved in water to create a solution of the aqueous ions. That looks good to me. What have we got here? Well, it's not an ion. Remember, it's a mole of gaseous ions. This is a mole of gaseous atoms. So this would require the first electron affinity of chlorine and then the enthalpy change of hydration. So that would be 2 things. So this one. This one's even worse. They're not even atoms now. So like this would be the bond enthalpy of chlorine and the first electron affinity and the enthalpy of hydration. So not that one. And then this one, well, it needs even more than this assumed. So yeah, definitely not that one. That was just a bit of nonsense. So 8. And then number 19, which ionic compound has the largest value of lattice enthalpy? So remember, the ones with the largest lattice enthalpies would be small ions with big charges. So that's what we're looking for. So if we break these down, so this is Mg2+, because magnesium's group 2 and sulfur's group 6, so it's 2-. Mg2+ again, and now O2-. Now O2- is a smaller ion than S2-, because it's got one less shell. So I can rule that one out, because they both got the Mg2+ in common, but oxide is smaller than sulfide, so it'll form a stronger ionic bond. Calcium 2+, and then we've got a huge Br- ion. So again, well, calcium is bigger than magnesium, bromide is much bigger than these two, and it's only a 1- charge, so that'll be a no-no. And then Na is just 1+, F is just 1-. Nice small ions, but the charges aren't as big as in these ones. So I'm going to eliminate that one. So here we've got two nice small ions. Remember, the magnesium ion is actually smaller than the sodium ion because they're both isoelectronic. They both got 10 electrons, 2 and 8. But the magnesium's got a bigger nuclear charge, so it will pull those electrons in more tightly. Oxide versus fluoride, well, again, they'd both be isoelectronic. The fluoride ion, okay, that would be smaller because it's got a bigger nuclear charge. However, the oxide's got a bigger negative charge, so that's going to form stronger ionic bonds. So based on that, I'm going to go with B. Bigger charges are going to beat those smaller charges there, and these are going to form nice strong ionic bonds due to the strong attraction between those small ions with large charges. Number 20 then, so let's go into the rate section now. So which experimental methods could be used to observe the progress of the following reaction? It's one that you might not be entirely familiar with. Hopefully you come across dichromate, remember, in the oxidation of alcohols, and if we remember, that's an orange colour. And then it forms green chromium 3+. So there is a colour change, so there is going to be a change in colour. It'll go from orange to green. We're also making brown iodine here, so it's definitely going to be a colour change. Might not be particularly easy to follow, but if you had a colorimeter perhaps. A change in mass, well, there's no gases being produced in this reaction, so you'd expect the mass to remain constant because nothing's actually being lost from the reaction, so I'm not reckoning on a change in mass. A change in electrical conductivity, I'm basically looking for a difference in the kind of number of ions or the sort of overall charges present. So here I've got a 2- and I've got a sort of 6 1- ions. Here I've got 14 H+ ions. Whereas over on this side, I've only got 2 chromium 3+ ions. So looking at this side, I've got 1, 7, 21 ions on this side. This side, I've only got 2. So basically, the electrical conductivity will decrease as this reaction proceeds because there will be fewer ions around to carry the charge. So there will be a change in electrical conductivity. So I'm going to go with 1 and 3. So I'm